Assalamu alaikum. Welcome to the third lecture of chapter 6. Chapter 6, of course, is mechanical properties of metals. We will start by briefly reviewing what we did in lecture 2. And after that, today we will cover the topics of ultimate tensile strength, ductility in percent reduction in area and percent elongation. We will compare some stress strain curves for different materials, and we will try to learn about what is true stress and true strain. And of course, these are, the ultimate tensile strength and ductility, etc., are also mechanical properties. So we will build up on the mechanical properties that we did last time. Let us start by quickly going through what we covered in lecture 2 of chapter 6 last time. We talked about Poisson's ratio, described it with a. We talked about shear stress and shear strain and their units and their definitions. We gave you the three material properties of elastic modulus, shear modulus, and Poisson's ratio for some of the materials which are commonly used in engineering applications. Again, we described a figure about shear stress and so on, and how any oblique stress force can be divided into a tensile and a shear component. We again went through describing tensile strain and shear strain and so on through other figures. I gave you some general applications of combined loading and so on, and then simple tension, torsion, simple compression, bending, and how the different stresses are related to each other. Then we started describing the tensile test. How do we actually measure the mechanical properties from a tensile test? We talked of the load cell, of the extensometer that we use. We gave you a general figure of a common universal testing machine or a tensile testing machine. Other figures, more realistic, of an actual one which is used in experiments in solid mechanics lab. More general schematic of the moving crosshead, of the load cell, of the specimen, of the extensometer. And then a close-up of a piece which is fixed into the grips and on which the extensometer has been attached. We showed you the exact dimensions of a round bar and a flat bar that is used for tensile testing. And then we showed you that after the force and deformation readings are available from the machine, then you divide the force by the original cross-sectional area, you divide the changing lengths by the original length, and you get a stress-strain diagram. And this is a typical stress-strain diagram for any metal. Here the metal is a very high strength aluminum alloy, 7075 T6. And on one side we have PSI units, on the other we have megapascal units. Then we started describing the mechanical properties that you can derive or extract from the stress-strain curve. The first is the modulus of elasticity, or Young's modulus. This is the relationship. It is a linear straight line and so on. Here is a comparison of the Young's modulus values of the four basic material categories: metals and alloys, ceramics, polymers, and composites. Then we talked of yield strength, that how do we define it, where is it exactly there, and that if there is no clear-cut yield strength available, then we find it by a 0.2% offset yield strength method. And here was the graph, that if there is a definite point at which the straight line ends and the curve starts, then that point is already the yield point. But if it is very smoothly merging into the nonlinear part, and you cannot decide where exactly is the straight line ending, then on the strain line you mark 0.002 or 0.2%, right? 0.2% is 0.002, same point. So you mark that point on the strain line and then make a line parallel to the elastic region, a straight line, and wherever it cuts the curve, there you mark, and there you see that, okay, this is the offset yield strength. So there is, this is where we stopped last time. And now let us start with today's lecture. Now just a reminder, because all of you are always interested about the quiz and so on. So quiz 1 will be on Tuesday. It will be in class, so that your class starts at 4:15, so it will start sharply at 4:15. The coverage I have told you is chapter 1, introduction full, and chapter 6, mechanical properties before ultimate tensile strength, right? So whatever we covered just now, whatever we reminded you in lecture 2 just now, this is the part of chapter 6 that we will cover. The pattern could be multiple choice questions, true false questions, short theory questions, numerical problems, etc. If they are multiple choice or true false type, then they will be completed online on Moodle. You have experience with so many courses last semester, so directly on the Moodle you solve it. If there are other questions, short theory questions, any numerical problems, then you do it on blank pages. You are ready with blank pages. And on each page, you write the question number, your name, and the ID on each page, right? The top page, the back page, everywhere. Then once you finish, then you scan it as a PDF. Don't scan it as a picture. Don't send me the Word file. It is very cumbersome. So whatever solution you have, whether it is 1 page or 2 pages or something, you scan it as a PDF and upload it to Moodle, right? And as a suggestion, I told you that there is a package called CamScan. Maybe you already have it. It is a very popular scanning software for mobiles. So download it on your phone. Then you can very quickly scan and you can get a very high quality and save it as a PDF. We also told you that the questions will be sequential. I will not, if there are 3 or 4 questions, I will not load all the questions on Moodle at the same time. I will load one question, give you time, you finish it, you submit it, and then I will open the next question. It will be sequential in nature, just to make sure that everybody is given the same chances and so on. And I will send you either the property values or tables in the questions or as an adjacent sheet, and I will send you a formula sheet. So in your standard exams, when we are doing it in the classroom, that is how we do it. We give you a formula sheet and tables and values together with your quiz, and you have no access to your books, your class notes, and so on. So similarly, you have written an honor statement, you have signed it, you will upload it. I have told you that you will not use the book, the class notes, the internet sources, or help from any others, right? So this is how any good exam should go ahead. You are the best of the best in Oman, right? In Sultan Qaboos University, only the topmost students from the whole country get into it. And then especially in Sultan Qaboos University, when you get into the College of Engineering, you are the top of the top. So you are the best, you should hold that. And honesty and integrity and character are greatly important things. So, right, so though you are at your home, we are not looking at you, but some very high power is looking at you, right? And you cannot hide anything from there. So please make sure that you use only the formula sheet. You do not use the book and so on. And this will make you strong, and when you, this will be good for your future exams and so on. Okay, so back to the stress strain diagram. We have already described it to you. So yield strength, again, as I showed you the previous chart, this chart is also from Callister. Callister is a very good book in this regard. So we have yield strength here. The unit is megapascal. The unit is megapascal. Metals and alloys, ceramics, polymers, composites. Okay, this is the yield strength. Yield strength. Once again, if I ask you now, you have gone through the previous lecture, what is the yield strength? If you have to say one sentence, what will you say? What is the yield strength? Those of you who are saying that it is the point where the elastic deformation ends and where the plastic deformation begins, then you are right. It is that point. It is the end of the elastic region. It is the beginning of the plastic region. Okay? So it means that yielding means that it has started to deform permanently. Right? Now, if you, I don't know if you notice here, one thing which is very clear is that the yield strength of metals and alloys is pretty high, and of polymers, plastics, is pretty low. Some metals like pure tin or some aluminum alloys are low. They are as low as good strength polymers, but all the other metals are very high. But what is this? What is this? Hard to measure. Don't read further. Hard to measure. Why is it hard to measure for ceramics? Can you, without trying to read anything here, can you tell me why are no values of yield strength given for ceramics? Just think, don't read. You see, if you have already read the next line, then it doesn't matter, right? You are not using your brain, you are not taxing it. You should be very clear that no, I will not read, I will try to answer from my own mind. So for ceramics, why is it hard to get the value of yield strength? Why are no yield strength values reported for ceramics? Anybody? What is the most important property of ceramics? They are very hard and very strong, and they are brittle. Do you understand? Two different things. One is that they are very hard and very strong. They are much harder and stronger compared to many normal metals. This is one side. The other side is that they are brittle. And I tried to explain to you earlier, it is not that if something is very hard, it will be brittle or not. Something can be very small hardness and still brittle, and something can be very high hardness and still brittle. Brittle simply means what? Yes, you are right. Brittle simply means that there will not be plastic deformation. There will not be large plastic deformation. It will not be very ductile. Right? So that is the problem. If it is a strong ceramic material, then the strength is high. The line on the stress strain diagram, the line goes up and up and up and up. But suddenly it finishes in a straight line. It does not go into the large deformation. So if it does not go into plastic deformation, there is no yield point. The end of the elastic region is there, but you cannot call it a yield point.